So, we're going to look at the tension that occurs in those wires thanks to an object pulling down on them. All right? So when an object is suspended between wires or ropes or chains or whatever, its weight pulls down on those wires and two triangles are formed. Okay? Two triangles are formed. The object itself is motionless once it's held there. The picture hanging on the wall, at least you hope it stays motionless and doesn't fall, right? What does that mean the net force on the object is? All right. So the net force has to be 0. So the key to these problems is understanding that the X and the Y components balance out. We've been working on finding all X components. So everything one direction in the X is balanced by everything the other direction in the X. So forces to the left must be balanced by forces to the right. That's your x-axis. And forces pulling down must be balanced by forces pushing back up. So forces up equal forces down. And we will be working this mostly from the forces up equal forces down standpoint. These get very complex. I'll keep them doable. All right? Okay. So down here is a picture like you might have hanging on a wall. And behind the picture, as you all know, there's probably a wire. And we put that wire over a single nail. And the wire sags such that you have a triangle formed on each side. So I'm kind of going to draw it over here. So here's our picture. What is it that the wires have to hold up? The what? Not what, the force.
Gravity.
When you say gravity, what do you mean?
Weight.
The weight.
But isn't like two strings attached to the painting it's like a nail in the wall, so it's instead of this exactly.
Yeah. So what you're saying, it's like this. Same difference. I can draw it that way if you want me to. But either way, they are holding up the weight. Okay? So you get two triangles that are formed. These have tension in them. Tension is a force. We're going to have tension on the right-hand side, tension on the left-hand side, or you can use an A or a B like my little clown picture over here. There is an imaginary, if you will, X on the right and an imaginary Y on the right. You're breaking the wire itself into its X and Y component. Same thing on the left side. There's a Y value on the left and a Y value on the right. Oh, I should put an L there. Make that an L. Left. An X and a Y on the left, an X and a Y on the right. Is everybody with me? Okay. When the object is centered, our two triangles are similar. So these angles are the same. The triangles are similar. Okay? So the X value on the left must be balanced by the x value on the right. And the weight of the object is the down force, must be balanced by the up force on the left, which is y on the left side, plus the up force on the right, which is y on the right side. Does that make sense? Okay. That's the basics of what we're about to do.
Why doesn't y on the left and y on the right equal like the x's do? Why do you have to add?
Wait, does it say x equals x?
You're going to see that in a minute. I'm going to do 2 examples, and I think it'll answer that question. Okay? Sometimes they're equal and sometimes they're not.
Is that because they're similar or not?
Right now they're similar, so they will be.
Okay.
Okay, that's only when the object is centered. That's where we're going to start. Okay, so let's do an example. Here's your baby picture. Your picture, let's say, is 50 newtons and centered between wires A and B. Find the tension if the angle is 100 degrees as shown. Okay, so here's my picture over here. If there's 100 degrees between the 2 wires, we're going to find the tension in the 2 wires. So I'm going to redraw my picture. Here's side A, here's side B. This is 100 degrees. My picture's weight goes down here, so that's 50 newtons. And I'm going to draw my little imaginary lines showing my x's and my y's on the left and the right. All right, so I've got 2 triangles that are similar, but I don't know an angle inside the triangle, or do I? I do. Which angle do I know? We know from here to here is 180, and if this is 100 of it, this is 40, and so is this. Okay? All right. So now all we know is an angle. But we know the triangles are similar, so the y on the left equals the y on the right, and we know that they add up to be 50 newtons. So each side holds up half of the weight. All right? When the object is in the center, the vertical supporting amount is half of the weight. So this side is 25 and this side is 25. Now we know enough to find the tension on both sides because the tension in A is the same as the tension on B. So I'm going to work on my right-hand side. Sine of 40 degrees is 25 over the tension on side B. I'm just using a B for that. So plug that in. 25 divided by sine of 40 is about 39 newtons. And that means the tension on side A is also 39 newtons. It's not that bad, is it?
No.
Yes.
You're not giving the angle.
I have to give you the angle. Actually, I'll always give you an angle so that you can figure them out. They can be solved without knowing the angle and going back, and that would be what you'd be finding.
Yeah, you'd have to.
But I would have to then give you enough information to know 2 sides of the triangle if it's the angle I'm having you find. Okay? All right. A real-life example down here. I've got 2 pictures of a couple of male gymnasts doing the iron cross. If you know gymnastics, that's not easy, is it? Well, what the heck makes it so hard? Why are they never smiling? Let's see, because it's hard. Let's see why it's hard. Now, this is actually a very complex stunt that they do, and you have to actually consider their elbows and rotations and all kinds of interesting things. We're going to keep it simple and just look at an overall tension in their arm. So, what would a male gymnast, you think, weigh? Let's keep a nice, easy number to work with. 150?
They're not that big.
They're little tiny guys?
They're probably 150, 160.
I don't really care. We're gonna work in pounds so that you all have a picture in your head of what this would feel like. Alright? If you just hang vertically and you weigh 150 pounds, how much does each arm hold up? 75 pounds each. So that's the minimum tension in each arm. Now as he starts to move his arms out a little bit and then a whole lot, let's see what happens to that tension. So we're going to have two similar triangles form. See the triangle here and the triangle here? And his weight is 150 pounds. So these are similar triangles. I'm going to redraw the triangle out here for his arm on the left side of the picture. So this is the tension in his arm. How much weight does this side have to hold up vertically? 75 pounds. Same would be true on the other side. Now I would need to give you an angle, but this is pretty far down, isn't it? So what might that angle be? It's going to be more than 45 based on the picture. So 60? All right, let's give a 60-degree angle in there. And let's find the tension in his arm. Sine of 60 degrees is 75 over the tension in his arm. If you plug that in, 75 divided by sine of 60, that's only 87 pounds. No problem, right? I bet most of you could do that. Now let's look at the guy over here. Do you see the triangle that I'm drawing with each arm?
So when the triangle becomes smaller, it becomes harder to move.
That's what we're going to look at. So now this angle compared, he's getting more and more horizontal. What do you think that angle looks like? Like this?
Wouldn't your other
5 or 10 degrees? Say that again?
Wouldn't the triangle on the left be facing the... Yeah.
Oh, did I draw it backwards? I did. You're right. Sorry. I was talking while I was drawing. All right, let's call this a 10-degree angle over here. All right? It still has to hold up 75 pounds vertically. So now let's find the tension in his arm. Sine of only 10 degrees equals 75 pounds over tension. And it's up to 432 pounds. That's a little trickier, isn't it?
But that's not your weight. It's not understanding how it works.
It's all about these angles. And it is holding up your weight vertically. It becomes more and more difficult to vertically hold up your weight the closer and closer your arms are to horizontal. Do you like videos? I just showed you a video. Alright, so there's lots of real life examples of that. Engineers have to think about these things when they build any object that has to support weight pushing down on it. Even at a microscopic level, there's going to be angles formed, and they have to consider those tensions. Okay? What about when the object is not in the center? Okay? When it's not in the center, things work a little bit differently. So let's say you have a sign hanging between wires, but it's not in the middle. So let's say this is a sign that we have held up and it's not in the middle, so you get slightly different angles. A 30-degree angle on this side and a 20-degree angle on this side, thanks to the fact that it's not in the middle. So I might tell you something like this. This sign might weigh 100 pounds. And I might tell you that this side, the tension on the left, is 175 pounds. What is the tension on the right-hand side? Okay? Now, what's different this side is that the Y on the left is not going to be equal to the Y on the right. They're not going to hold up exactly half of the weight because the triangles are no longer similar. So, what do we do first? We can find out how much weight the left side holds up because we have an angle over here and the hypotenuse. So sine of 20 equals the Y on the left over the tension on the left. So 175 times the sine of 20 is 60 pounds. Okay? And the Y on the left plus the Y on the right, the forces up, still have to hold up all 100 pounds. So if 60 is held up on the left, how much is held up on the right? The other 40. Now we can solve for tension on the other side. Sine of 30 degrees is 40 over tension on the right. And tension on the right is 80 pounds.
Will you always tell us if it's centered or not?
I would have to tell you if it's centered or not, or give you angles, something to let you know. And that is the last type of force vector problem that we're going to do.
So you can tell it's not centered if the two angles aren't the same?
Yes.